Alrighty, Mr. Hess, back with another geometry lesson for you. We're up to uh, lesson 3.3, which is titled Prove Lines Are Perpendicular. So one of the first things I want to do then, as you can see on my board back here, is cover the definition of what it means to be perpendicular. So by definition, objects are perpendicular if they intersect to form a right angle, a 90-degree angle. Okay, so in this picture here, if AB and BC are in fact perpendicular, they often will indicate so in a picture, by the way, by putting a little square box down here in the corner. And the symbol for this, when we go to write this, we would say then that segment AB and segment BC here are perpendicular. So the symbol for perpendicular, as you can see here, is an upside down capital T. It's literally illustrating, the one line here and the other line here intersecting to form that 90-degree angle we talked about. Kind of like when you call timeout, you do that. You take your hands and make them perpendicular. It does not have to be segments that are involved. This could have just as easily been a ray. You could have had ray BC here. You could have made this into a line. You could make it line BC. So it could be lines, it could be rays, it could be segments. It could even be planes, believe it or not. Here's an example over here where I've got a segment and a line intersecting, again, to form a right angle here. So we could say they are perpendicular. So again, I would write this one by saying segment DE is perpendicular to line FG. But in this example, I just wanted to show you that initially over here, I had started, remember, with the segments that look like this. So I wanted to show you that by definition, all they have to do is form a right angle, a 90-degree angle, just one. Okay, but sometimes you'll have more. Like when I drew this across here, now I had two of them. And in this picture, I hope you can see I have not just one, but 2, 3, 4 of them. But again, all it takes is one 90-degree angle to say they're perpendicular. Okay, but there may be more than one right angle. Okay, so that's what I wanted to start off things with, is a definition of perpendicular. The next thing I want to be able to cover here then is a theorem called the perpendicular bisector theorem. Perpendicular bisector theorem. Okay, so let me clear some space here. And in the perpendicular bisector theorem, it basically says this. If we've got a segment, maybe we call this AB, and if we construct a perpendicular bisector of it. Okay, now, if you piece together that name here, perpendicular bisector, as you can see by the name, it's going to be perpendicular. So as we just discussed, it's going to have to form a 90-degree angle. And we know from the past that to bisect something means to cut it exactly in half. So if we take this AB, if we find the dead center middle of this one where it would cut this in half, maybe we call that point C. And through that point C, then we're going to construct a line. Technically, a perpendicular bisector could be anything like a segment, line, or ray. But I'm going to go ahead and make a line that goes through right there at C. So I'm going to move C off to the side there because I'm going to go right through C at a right angle. Okay. That line that I just made is what we call the perpendicular bisector. Okay, so that part, the perpendicular bisector, is that line. Okay, the bisector is the one doing the cutting. So this guy right here, if I put a point up here, for example, and call it maybe point D, then that line DC is my perpendicular bisector because it went right through the dead center middle, bisecting that segment, and it did so at a right angle, so it's perpendicular. Now, according to the perpendicular bisector theorem, what they say is that if you pick any points along this perpendicular bisector, like that point D right there, and then if you draw a segment from D back down to the ends of the original segment AB, so DA and DB, and if you do that, as long as the point D up here was on the perpendicular bisector, these two lines I just made are guaranteed to be congruent just like these two were. See how CB and CA here, those two are the same? Okay, this is now guaranteed to be the same as well according to our theorem. And again, you could pick any point along there, along this perpendicular bisector, and that will work. You know, you could even pick a point down here. I'll use another color, and let's call that one point E, for example. So if I drew segments now from E to B and E to A again, just like the original segment, how it was bisected, these are going to be the same as well. So this length will match that length. And you could keep doing this over and over and over again. You know, I could pick a point in here. Call that one maybe F, and FB and FA will be the same length. 1, 2, 3, 4, 1, 2, 3, 4. Okay? So any points along there on that perpendicular bisector are going to create additional segments that would match if you picked any points on there. So that's the perpendicular bisector theorem, and it also has a converse that is true as well. Okay, so the converse would flip things around. Now keep in mind, this one originally said if DC here, that line CD, DC, this line along here, if it was both perpendicular to AB and if it bisected AB, so and if AC here and BC here were congruent, we came up with a conclusion then that any of these additional points we picked were going to be the same. I'm just going to pick one of them out here. You know, like for example, the DA and the DB. So then DA was congruent to DB. Okay, now when we take a look at the converse of this, of the perpendicular bisector theorem, we're going to be doing some switching. Remember, a converse takes a statement and switches the hypothesis and conclusion. The if and the then get switched. Okay, so what we're going to do then is we're going to say then that if DA and DB are in fact congruent, okay, and they're already on that line, okay, but we're going to keep the perpendicular part. So really we're just going to switch these two. Okay, so if I take this idea and switch them, we're going to say if, in the converse, we're going to say if we know these lengths were the same and that was a right angle, then it's guaranteed to bisect it. We could even switch this one with that one and say that if we already know they're a right angle and these are the same, then that means these will be the same, the AC and the BC. Okay, so the converse really just switches the idea. It works forwards or backwards, you might say. Kind of like a definition, how a definition works forwards or backwards. So this theorem works forwards or backwards as well. Okay, there was one other theorem that I want to cover in this section, and then I'm going to jump into some problems that are similar to, or that would utilize this theorem. Okay, and the last theorem I want to cover yet is the perpendicular. It's actually not a theorem; it's a postulate, I should say. Is the perpendicular postulate. Perpendicular postulate. Okay, and it's kind of like the parallel postulate that we covered just recently. If you remember right on the parallel postulate, we said, you know, if you have a line and a point not on the line, the parallel postulate said there was only one and only one line that would be parallel to that one right there. Well, the perpendicular postulate is just going to change from parallel to perpendicular. And again, it says really the same thing. It says there is one and only one line that we could draw. Here, I'll draw it in a different color here. But there's one and only one line that we could draw that goes through that point, yet will stay perpendicular to this line. Remember, to be perpendicular means they should form a right angle. So there's the one and only one line I'd be able to draw that went through that point, yet stayed at a 90-degree angle here to that line. That's really only useful for when you're constructing your own drawings. You know, if you want to make a line be perpendicular to this line going through that point, there's only going to be one line that exists. All right, so let's jump into some problems here that we can utilize. Not necessarily this idea, but the perpendicular bisector theorem. Okay, so up here I've got a problem where we're trying to find x. Okay, and x being this missing side length over here. I want you to recognize, though, that I've got a segment running down here that is both perpendicular at a right angle, and I want you to notice that it is splitting this into two equal halves, 9 and 9. So that would make this segment here running down through the middle the perpendicular bisector. Okay, so according to the perpendicular bisector theorem, if that comes down at a right angle and splits this, then that means this point up here, as we go from here down to each end point of that segment, that those lengths should match as well. So I know this 14 should match this x. So as you can see, this is a very easy problem. If you recognize the perpendicular bisector, then you know that these have to match, and x equals 14. Boom, done. Okay, let's try another one. We'll call this one problem number 2. Okay, and on this one, again, I've got a segment running down at a right angle. On this one, I'm going to show you this time, instead of having x be one of these up here that I had to find, this time I'm going to give you those. This is 20, that's 20. And on this one, we're going to call this down here x from here to here, and then this portion is 7. Okay, so on a problem like this one, now we're going to make use of the converse of the perpendicular transversal theorem. Okay, remember I told you that perpendicular, I said transversal, I'm sorry. The perpendicular bisector theorem. Okay, the converse of it works as well. So if we already know that those two sides matched here, where I made that conclusion here, but if I already know it here, and I know that this is a right angle again, then I know down here, like I already knew on this one that these matched, now I know these will have to match as well. So if these match, if that's a right angle, then these down here have to match. So again, an easy problem here. That one's just x equals 7. All right, now I've got a new problem up here, problem number 3. And on this one, again, I want you to notice the segment running down the middle is perpendicular. It is also splitting this down here into two equal halves, making it a perpendicular bisector. And according to our perpendicular bisector theorem, then not only will these two match, but this and this have to match. So you can see on a problem like this one, solving for x is going to be a little more elaborate. It wasn't so easy like the previous ones where you could just, automatically list your x. Here you're going to have to come up with an equation stating that 3x plus 10 over here is equal to this segment over here, the 7x minus 22. And then you got to solve for x. Okay, we've got an x on each side, like a sheriff and a bandit. So I'm going to subtract 3x from both sides. Now I've got 10 equals 4x minus 22. I want to keep adding and subtracting as long as I can. So my next step here would be to get rid of the 22 by doing the opposite. Add 22. Whatever you do to one side, you got to do the other. That cancels, so we have 4x equals 32. And then as a last step here, we're going to do some division. Okay, we divide by 4 to get rid of the 4 in front of the x. So now the x is finally by itself, and 32 divided by 4 gives me 8. So when they said find x, I'm done on this one. I can see my x is 8. All right, I got another new problem up here for you, problem number 4. And on this one, as you can see, they gave us some information over here. They tell us that this segment AC is the perpendicular bisector of BD. Okay, so again, that tells us two things. It's perpendicular and bisects the segment. Well, the perpendicular part's already been indicated here in the picture with the right angle. The bisecting part means then that this is going to equal this. Now you'll notice they also gave you this total measurement of 20, which means then that each of these equal halves would have to be 10 apiece. I'm simply dividing 20 into 2 equal pieces. Okay, now on this problem, they want us to find this x. There's no matching value over here, which it would match. I do know that this will end up being congruent to this side as well. However, again, I have no measurement over here. Instead, this time they gave me the perpendicular bisector's length. They told us this segment running down the middle here is 24 in length. Okay, so on a problem like this, really what I want you to be able to recognize is that the perpendicular bisector, when it came down and when you capped it off over here with this AD, it creates a right triangle. See the right triangle? And all right triangles then have a very famous theorem that I know a lot of you are familiar with that deals with the side lengths. In fact, as I start to write the formula for it, a squared plus b squared equals c squared, I'm sure it'll come to mind that that is the Pythagorean theorem. Okay, and if you look, we do have 2 out of the 3 sides of our right triangle there. Okay, so we can use the Pythagorean theorem then, in this case, to find that one last missing side. All right, so let's do that. The 24 and the 10 are both legs. The legs are always the 2 that make up the right angle itself. Okay, so 24 and 10 are going to go in for the A and the B. Okay, directly opposite of the right angle is always the longest side on a right triangle, known as the hypotenuse. And that's the C part over here. So X is our C. So it's going to already be by itself over here on this side of the equation. All right, so now let's go ahead and solve for this x. So we got to do some math here. 24 squared. I believe that that's like 676. I don't know. Hold on. 24 times 24 is, it's 576. There we go. 576 is what we get when we square 24. 10 squared is 100. That's an easy one. These are already together on this side, kind of like a sheriff and a deputy. So they're like terms. Go ahead and combine them to get 676. But that's x squared. Okay, be careful. I want x, not x squared. And then, look at the problem too. That would not make sense for a final answer. How could this only be 10, that only be 24, and then this side be 676? No. We need to get rid of the square yet to get x by itself. And again, in algebra, you do the opposite to get rid of things. the opposite of squaring is square rooting. So we're going to do the square root of each of those sides, and if you do the square root then of 676, this one comes out to a nice whole number for you. It comes out to 26. So there's our missing length of this side, and we had to get it by using the Pythagorean theorem. Okay, so keep that in mind. When you work with perpendicular bisectors, by nature, they're going to be splitting things into a lot of right triangles. Okay, now I have one more theorem that I want to cover in this section yet, this lesson. And it's the perpendicular transversal theorem, which I accidentally mentioned earlier in this video. But in this theorem, we start out knowing a couple of things, and that would be our if part here. But if I already know these two run parallel, so M and N are running parallel. And if I already know that M and T are perpendicular, so M meeting T, as you can see, I marked it right there at a right angle. Well, then, according to our perpendicular transversal theorem, we could take that right angle and essentially transfer it down here as well. We could say that that has to be perpendicular as well. So N and T have to be perpendicular. It is a theorem. It is something we can prove. And if you look, for example, if I were to call this angle 1 and this angle 2, 1 and 2 are at each intersection. We've got the parallel lines. So from our previous lessons, if you remember right, these two angles are a pair of corresponding angles. So, and we knew if lines were parallel, corresponding angles should match. So you could justify this theorem using, just that idea alone right there. That previously we had learned that according to the corresponding angles theorem, I'm sorry, that was a postulate as well. The corresponding angles postulate, these two angles have to match. So if one of them is 90, the other is. But that's our perpendicular transversal theorem. Okay, let's put this idea to work in a problem here yet as well. So give me a sec, I'm going to set it up. Okay, as I had just mentioned, I just covered this perpendicular transversal theorem. And then in the textbook, they got a problem right below it here. It's task number 5 here, and they want you to find the length of the bridge supports indicated by PQ and RQ. The measurements are in feet. And if you look, I know it's kind of hard to tell on here, but can you see there if I zoom in nice and close here? We're finding PQ and QR, those two lengths along there. Okay, and they do indicate a few things that are given to us. For example, they give us that PS and RS are going to be congruent in this picture. So that's these bottom pieces, PS and RS. And they do indicate that we have a right angle right here. So it's perpendicular for this part right here is perpendicular to the QS. And they indicate that the lines running along here and along the bottom are parallel. You see the arrows that look out of place right here and here. Okay, so I'm going to do the same thing. I'm going to take all that given information and find those lengths like they said. But I put it up here on the dry erase board. So that'll be a little easier for you to see instead of in that picture that had that whole bridge in the background and everything, which made it hard to see. So again, some given information. We were given a right angle here. We were given that the lines running through here and here are parallel. And we were given that PS, this segment, is congruent to SR. Okay, so we can, on a problem like this, we can utilize that perpendicular transversal theorem that we just covered. Because in the perpendicular transversal theorem, we said that if these lines are parallel, and if this transversal is perpendicular to the one parallel line, then it has to also be perpendicular down here to the other parallel line. So by that reasoning, we can indicate that we have another right angle right there. Both of these are right angles. Okay, if you're wondering, well, why is that important? Well, it comes into play because now we can kind of ignore the top parallel line here. You know, if I kind of ignore that idea now, I'll just erase it out of here. By letting us transfer that right angle down, do you see that now this is just essentially becomes another one of our perpendicular bisector problems. See how this is now perpendicular down here as well, and it bisects that. And according to our perpendicular bisector theorem, that not only are these two pieces going to be congruent, but now I know this out here and this out here are congruent. And if those are congruent, then I could set these two equal to each other. I can take 8x plus 31 and set it equal to the 12x minus 5. And I could use that to solve for x. I've got an x on each side like a sheriff and a bandit. I'm going to get rid of the weaker one, so I'm going to subtract an 8x from both sides. That's down to 4x then over here. Bring the rest of it down as well. We got a 31 equals a minus 5 over there. Continue to add and subtract as long as you can. So at this point, to get this x by itself, I'm now going to add a 5. So that'll cancel. Whatever I do to one side, I got to do the other. So we're up to 36 over here and just a 4x over here. Now I could get rid of that 4 since it's being multiplied by dividing. When I divide by 4, you can see that I get x equals 9. Now you've done all the hard work. Don't stop there. Okay, some of you might get a little happy and like, oh, yay, I got 9 as x. Okay, but they wanted us to find the lengths of PQ and RQ. And remember, I read over there that everything is in feet. So this was, 8x plus 31 feet. And that was 12x minus 5 feet. So if I just take my 9, plug them back in, now I'll have both of those lengths of PQ and RQ. And really, you only have to plug into one or the other because after all, they're supposed to be equal, right? So if you like to add, plug into that one. If you like to subtract, plug into that one. I kind of like to add, so I'm going to plug my 9 into here. 9 times 8 would be 72. 72 plus another 31 yet gets me up to 103. So 103 feet is what we should have got for both of these. Both PQ and RQ come out to 103 feet. Okay, so there's a problem where we utilized both the perpendicular transversal theorem when I had, remember that second one that was in here earlier that had the right angle that was also parallel to this down here. So I used the perpendicular transversal theorem to transfer the right angle, and then we used the perpendicular bisector theorem to say that the two sides out here were equal. Okay, now to finish things up, I'm going to finish with a proof. I want to give you some practice with proofs yet, since they will be proofs will be involved, for the rest of the semester and off and on throughout the lessons. Okay, the proof that I want to do is in your textbook here on page 94 here. And what it is, this is a proof of the perpendicular bisector theorem. Okay, so if it's a proof of the perpendicular bisector theorem, then the only thing you cannot use as a reason in this proof is the perpendicular bisector theorem. Okay, you can't use the theorem you're trying to prove. Okay, so if you look then at our picture here, we've got CD is given as being a perpendicular bisector of AB. So we want to prove then, since the theorem says in the end that AC here, that length, will have to match BC, that length up there. So that's our goal on what to prove here. Okay, so I want to just go through these steps, step by step here, just to show you how they got everything. I know they only have, like 3 things to fill in here with an additional question here, but, I want you to understand the reasoning behind every step, even if it's already given to you here. Speaking of given, okay, they listed their givens here in the first step, so they're just stealing that from up here. CD is a perpendicular bisector of AB. Given. All right, so in step 2, they mentioned that AD and BD have to be equal in length. So there's the AD, there's the BD. They had already marked it up here in the picture, but it's coming from the previous given statement that it is a perpendicular bisector. And within the definition of what it means to be that perpendicular bisector is 2 things. Okay, a perpendicular bisector is both perpendicular and bisects the segment. So this is the bisecting part. AD equaling BD. Those 2 halves up here have to be the same by definition of perpendicular bisector. And then in the next step, they even use that same definition again, but this time to state the additional information that angle ADC here is a right angle. It's 90 degrees. Okay, so if they wanted, they could have merged both of those into one step. You could have just put AD is equal to BD and then put a comma and then put angle ADC and BDC are 90. And all of it is by the definition of perpendicular bisector. Okay, so again, that name kind of gives it away. They have to be perpendicular and bisect. So the right angles and the congruent halves right here, AD and BD. All right, so that gets us up to step 4. Now in step 4, they're going to state that CD is equal to itself. If you look in the picture, CD is that segment running right down the middle. Okay, so they're saying that CD equals CD. Now any segment you could say is equal to itself, and you're making use of a certain property. Okay, so let's see if you remember your properties that I helped cover earlier when we started doing algebra proofs. We did a lot of those properties. And CD equals CD is a lot like when you look in the mirror and you see your reflection. See how they're identical, CD and CD? So it's just like when you look in the mirror and see your reflection. So the reason is, have you figured it out yet? Whoop, there it is. The reflexive property. Okay? The reflexive property is the one that allows us to say then that anything is equal to itself. All right, so step 5 now. Step 5 wants to almost make a statement. You might think, oh, they're being Captain Obvious here. They're saying that in this picture, triangles ADC and BDC are right triangles. Remember, we had just indicated we have right angles both here and on the other side of it. So we want to point out that they're right triangles for a reason. But we're just using simply the definition of what it means to be a right triangle. Right triangles have to have right angles. Okay, but the reason we're pointing it out is for this next step. Because in step 6, you notice that they're saying that this side AC, which if we look back here, see there it is. AC is the hypotenuse across from the right angle of the right triangle. But AC is squared equals AD squared and CD squared. AD and CD then are the legs of that right triangle. See that right triangle on the left side? So they were saying basically the hypotenuse squared equals the 2 legs squared and added together. They did it again right below here, only with this right triangle on the right hand side. Again, across from the right angle is BC, so that's the hypotenuse. So they're saying the hypotenuse squared equals the legs squared and added. Okay, so BD is one of those legs, CD is the other. You may recognize then this setup. It's, again, a famous formula that I just showed you earlier in this lesson. Normally it's written as A squared plus B squared equals C squared, where the C they have over here on this side. Okay, but they want to know then what famous theorem here justifies that step? Well, I hope by now you figured it out. It's the Pythagorean theorem. Okay, again, that Pythagorean theorem is normally written as a squared plus b squared equals c squared. They just replace the a, b, and c with different side lengths. So it'd be like there's your a, there's your b, and then there's your c on that side. All right, now they say they're going to do a substitution next to get this statement here. Okay, if you look carefully, you can maybe figure out how they did a substitution to get that. The AD squared and the CD squared, you see it back up here on this one right here? We had AD squared, CD squared. But on this side, initially we had AC squared. They've changed it to a BC. So that's the substitution that occurred. They took out the AC, they put in a BC. How can they do that? Okay, well, actually, sorry, hold on, let me back up, rewind just a little bit. Let me start that from scratch again. See how the CD matches this CD? They're clearly the same, right? CD equals CD. We had that stated back here in step 4, which is going to help answer this question, by the way. They want to know which steps combine to create this step 7. So if CD equals CD in step 4, then we know those two match. The AD and the DB, we know those two match way back up here in step 2. See how AD equaled BD? So if these are the same, these are the same, okay, then I can take the BC that was put in here. I can plug that in for the AC because I know that these are all the same here. Okay, so if this whole thing is the same as that whole thing, I could put BC in, okay, and in place of the AC, and that's how I end up with this BC equals AD squared plus CD squared. We're doing a substitution. And while we're at it, you could even plug the AC back in for the AD plus CD up here. Since AD plus CD equaled the AC squared, we can replace this part with the AC, and now we've got BC squared equals AC squared. They kind of flip that around so it looks a little confusing. Okay, but they simply did another substitution is what that is. Or if you'd like, you could say that in that step 8, if you like to say the transitive property instead, you could say that even, because you could argue it's a chain of events. After all, you could say, let me see here, you could do the BC equaled the DB plus, or I'm sorry, the BC equaled this, AD plus CD, the AD plus CD equaled the AC, so the AC goes in, and you get this. Okay? Now, there's one last step in this proof, and the last step, they explain here with this explanation. You could even just simply put that you're simplifying this, because they state here that if x squared equals y squared and x and y are both positive numbers, non-negative numbers, then you could actually do the square root of each side and get x equals y. So that's all they're really doing is the square root of both sides. Okay, you could even state that if you want over here. We did the square root. Okay, so when you square root the AC and the BC, you get AC equals BC in the end, which is what we were trying to prove. Okay, so again, when doing proofs, I'm going to be having you fill in missing steps, and as long as you can figure out, like we did over here, that your missing steps on this one were, for step 4 was reflexive property, 6 was Pythagorean theorem, and 8 was a substitution or transitive property, then you'll be okay on these proofs. Okay? I'm going to put one proof on your homework as well. So you'll have to make sure you look in the Google Classroom. I'll be attaching it. I had to make my own proof with a few missing steps. So make sure you find that in Google Classroom and complete that proof as well. That's all I got.